Pi Molecular Orbitals. We're going to break this lesson up into 3 parts. In this first one, we'll cover ethylene, which technically isn't a conjugated system, but will be the basis for where we go from here. And but we'll cover 1,3-butadiene. In the next lesson, we'll cover the allyl system. That'll include the allyl cation, the allyl radical, and the allyl anion. And then finally, in the third part, we'll cover the pi molecular orbitals of 1,3,5-hexatriene. Now, this lesson's part of my organic chemistry playlist. I'll be releasing these lessons weekly, so if you don't want to miss one, subscribe to the channel and click the bell notifications. All right, so pi molecular orbitals, these are molecular orbitals. So we visited those way back in chapter 1, and we saw that when orbitals from adjacent atoms overlap, they form molecular orbitals. So there's atomic orbitals form molecular orbitals. And in this case, specifically, we're going to show the side-to-side overlap of p orbitals. We're going to find out with conjugated system, you actually get many p orbitals spread across many atoms overlapping. But I want to start with just plain old ethylene and review a little bit here. And again, we're not going to look at any of the sigma bonds at all. We're just focusing on the pi system here. And when you've got a double bond here, so these 2 carbons are going to have p orbitals. And just due to their size, their inherent size, they're going to overlap in this side-to-side fashion. And that's what we refer to as pi overlap, you might recall. And when this occurs, if it occurs in phase, if the wave functions match, that leads to constructive interference and a lower energy bonding molecular orbital. But if it happens out of phase, if the wave functions don't match those signs, so then it's going to lead to the creation of a node and the creation of an antibonding molecular orbital, which will be higher in energy. So that's kind of the deal. In this case, for ethylene, if we look at the way we represent this, so generally we represent the creation of this molecular orbital really as the composite of 2 p orbitals in the case of ethylene, but really it actually is just a way of representing a larger reality, and we'll kind of point that out here in a little bit. But in this case, you should know that if 2 p orbitals are overlapping sideways like that, it's going to lead to the creation of 2 molecular orbitals. All right, so we'll draw them out like this. This lower one's going to represent what we're going to call psi 1, this upper one psi 2. And each of these orbitals can hold 2 electrons. Now, I'm calling them psi 1 and psi 2. Some books for pi molecular orbitals specifically call them pi 1 and pi 2. So whereas psi is really generic to any kind of molecular orbital. So you'll see it represented both ways. But I'm going to be consistent using psi, or at least that's my plan. I apologize if I use pi somewhere along the way, because that's how I learned it back in the day. But in this case, 2 p orbitals overlapping, that's why there's 2 molecular orbitals. But it's also why each molecular orbital is going to be drawn as a composite of 2 overlapping orbitals as well. So again, these aren't really representing individual p orbitals, but they're just kind of showing what individual p orbitals were overlapping to create this bigger reality. And again, this is just the way we represent it, but I'll show the bigger reality here in a second as well. A couple things we should note here on drawing these. For a p orbital, you always have a node right along the nuclear axis here, so right in between the atoms. There's always a node right there, and again, that's just where the wave function goes to 0, and you might recall again that for a p orbital, one side of it is positive, one side is negative, and it could be either way, and as the wave function goes from being positive in sign to negative in sign, that's not charge again, so you have to cross through 0, which happens at the nucleus. And so when you get this overlap here, so oftentimes we use a couple different patterns for representing this plus and minus. And again, this is just mathematical sign, not charge. So in one way is just to shade them different colors. And another pattern would just be to shade one and not shade the other. And we just need opposites. It's not like here blue is going to mean positive and green means negative. It's just one is positive, one is negative. We never actually specify which is which. Now, if on the adjacent p orbital, we overlap these in such a way that positive overlaps with positive and negative overlaps with negative. And again, we're not specifying which is which. But we say this is in phase overlap, and where they overlap then would grow. And so we represent this just simply by how they're overlapping there. So we're not getting too creative here. And this is our lower energy bonding molecular orbital. So when they overlap in phase, it leads to an amplified region right where they overlap. And if you look, if you are electrons, which is what's going to live in this orbital, you're negatively charged. And the nuclei are positively charged. You want to be as close to both of them at the same time as you can. And that's right in this region right here that's amplified. That is now the most likely place you're going to find the electrons. So the best place to find the electrons, where they could be closest to the positively charged nuclei, is also now the most likely. And so that lowers the energy. It also turns turns out that when you get this constructive overlap, the size of the orbital grows, whereas when we see destructive overlap, we'll say that the overall size of the orbital shrinks. So, and it turns out just larger orbitals are lower energy, according to the Heisenberg uncertainty principle, which you don't need to know. All right, so here's what we draw. This is our representation, but keep in mind that, again, this represents a more complicated reality. What really we have going on here. Let's draw this a little better. So what really exists is one big molecular orbital where we got overlap all along this region above and below that internuclear axis. And so this is actually what the molecular orbital would look like, but again, this is what we draw. And again, I just point this out. All these molecular orbitals represent these more complex realities. So, but we draw them like this, and it's kind of, again, instructive of just showing how do the orbitals overlap to create this. But this is what you're going to be on the hook for in drawing in your typical organic chemistry class. So just keep that in mind. But I wanted to point that out because this doesn't really have this isn't really two p orbitals right here. This is one molecular orbital, but the way we're representing it is kind of the composite of the p orbitals that we're overlapping to make it. But this is what it would really look like. So just keep that in mind. All right, so that was the in-phase overlap, but you could also do it the other way here. So you could also have it being exactly out of phase, plus overlapping with minus in both places here. All right, so when that happens, when plus overlaps with minus, when you go to add the wave functions right where they overlap, they cancel because one's positive in sign, one's negative in sign, and they add up to 0. And when that happens, it creates a node. And again, we'll represent this just by, like we're showing it right there, how it's overlapping. So, and we can see that because these aren't, the wave functions don't match, they're out of phase, that leads to the creation of a node. And sometimes we'll kind of just highlight that node by drawing a little dashed line right there to kind of signify that node and stuff like that. And usually we don't do it after the fact. Usually it's actually a helpful tool for drawing more complicated diagrams and stuff like this. And what you'll find is if you actually look at the number of what we're going to call vertical nodes on any molecular orbital diagram, your lowest energy molecular orbital is always going to have 0 vertical nodes. Now, because these are pi molecular orbitals, notice there's always that horizontal node. And that's why I specified not just say number of nodes, but really number of vertical nodes. So got 0 here, we got 1 here. And what you find out is as you go up in energy with molecular orbitals, you always start again with your lowest energy is 0, and you always gain 1 as you go up to the next energy level. And so we're going to find with 1,3-butadiene in a little bit, so because it's going to end up having 4 adjacent atoms with p orbitals, that'll be 4 overlapping orbitals, that there will be 4 molecular orbitals, and they'll have 0, 1, 2, and 3 nodes as you go up in energy. So I just want to lay the groundwork here. Now, a couple last things we've got to talk about. So in ethylene, we've got just that 1 pi bond, so it's just 2 pi electrons. And so if we put those 2 pi electrons, you fill them in the lowest energy orbital first, and that's where they go, inside 1 here. Now, a couple other things to note. When you look at your molecular orbitals overall, the lower half of them are going to be the bonding, the upper half will be antibonding, and when you only have 2, that's just 1 of each. And to signify those antibonding, we often put an asterisk right there just to make sure we realize that's an antibonding molecular orbital. Another thing we should note, and again, we've just got 2 orbitals here, so it's kind of a moot point here, but we often identify 2 particular orbitals that are the ones involved in chemical reactions. And one of them is called the Highest Occupied Molecular Orbital, or HOMO for short. So highest energy occupied molecular orbital or just highest occupied molecular orbital. You see it both ways, but HOMO is the abbreviation in either case. And it's just the highest energy orbital in your molecular orbital diagram that is full of electrons or has electrons. So, and then the one right above it, we identify as the lowest unoccupied molecular orbital, the lowest empty molecular orbital is usually the way we look at it. So, and that's this guy right here. And they're usually, one on top of the other. And the reason we identify these is that the highest energy electrons this molecule has, or at least the highest energy pi electrons, are these guys right here. And so if this molecule is going to act as a nucleophile and donate a pair of electrons to make a new bond, in all likelihood, it's going to be the highest energy ones it has, the ones in the HOMO. On the other hand, if this molecule is going to act as an electrophile and receive an electron pair, then in all likelihood, where do you want to put an electron pair? Well, you want to put it in the lowest energy empty spot you possibly can, which would be the LUMO. And so together, together, we collectively call these the Frontier Molecular Orbitals. And again, they get a special name because they're the ones involved in chemical bonding. Notice we did this back in Gen Chem as well. We talked about the valence electrons, the outermost shell, and then all the core electrons, all the inner shells. And the reason we kind of segregated it that way is because the valence electrons were the ones involved in chemical reactions, in chemical bonds being broken and formed. And so, same exact kind of thing here. The HOMO and LUMO, the Frontier Molecular Orbitals, are the ones typically involved in chemical reactions. That's why they get special identifications. All right, so this is essentially what I wanted to cover here. But again, this is something we did cover back in Chapter 1, not quite in this level of detail, but we did talk about what pi overlap leading to both bonding and antibonding molecular orbitals would look like. So, but now we want to move on to talking about 1,3-butadiene instead. And so with 1,3-butadiene here, if you actually draw it out, you got a pi bond here on the left. So you got overlapping p orbitals there, but then you've got one on the right here as well. So you're going to have, drew that big just to make it work, but you're going to have overlapping orbitals here as well. But just due to the size of p orbitals, it also means you end up having overlapping p orbitals in the middle, where our lovely Lewis structure and bond line structures don't show any overlap, but there is overlap there. And as a result, you actually end up with 4 overlapping p orbitals, not just 2 like we saw over here. And this has 2 consequences. With 4 overlapping p orbitals, well, now instead of having 2 molecular orbitals, you're going to have 4 of them. And instead of drawing each molecular orbital as the composite of 2 overlapping p orbitals, we're really going to draw them as the composite of 4 overlapping p orbitals. So that 4, is going to be kind of shown up in 2 places here. So we're going to have, in this case, we'll draw it as psi 1, psi 2, psi 3, and psi 4. So we'll just draw the energy levels first. In this case, we can take this even a step further. So the lower half are bonding, the upper half are antibonding. So in this case, we'll signify those again with an asterisk. So we can also see that we've got 4 total pi electrons in those 2 double bonds. And so we can fill in psi 1 has got a full set, and so does psi 2, both full orbitals. And so now we could also even identify the HOMO and the LUMO. So the highest occupied molecular orbital, in this case, is psi 2, and the lowest unoccupied molecular orbital is psi 3 antibonding right there as well. Cool, so before we've even drawn a picture, you can already fill in the energy diagram and identify where the HOMO and LUMO are. You can even take this a step further. If you recall, we talked about the number of vertical nodes. So, and in this case, your lowest energy molecular orbital always has 0 vertical nodes. And again, every energy level you go up, you gain another vertical node. So psi 2's got 1 vertical node, psi 3 star will have 2, and psi 4 will have 3. So it always works out that way. And that's often a useful tool for helping us draw some of the more complex diagrams. Now, again, we've got 4 overlapping orbitals here. And so when we go to represent these, we're going to represent them as the overlap of 4 p orbitals. But again, it's going to actually depict a more complex reality. Let's take a look at what these look like. All right, so I've set up the framework here for each one of these. So again, because there's 4 overlapping p orbitals in our conjugated system here, so as a result, we have 4 molecular orbitals we need to draw, and each of those 4 will be represented as coming from 4 overlapping p orbitals. So again, this represents one big molecular orbital, but again, it's kind of, we're representing it by the 4 p orbitals that actually overlap to create it. All right, so in this first one here, we're going to have no vertical nodes, none whatsoever, and all the wave functions are going to be in phase all the way across. And that's going to be true always of your lowest energy overall molecular orbital for any of these diagrams we're going to draw. And again, this actually represents, again, a more complicated reality here. The reality it's really representing is this big smear of electron density spread across all 4 atoms. And so in this case, the electrons here in psi 1 get to see 4 different nuclei. So they're attracted to all 4 positively charged nuclei, which significantly lowers the energy. And that's why it's so low in energy here. So there's delocalization across, a wide region that sees multiple nuclei. So that's what's going on here. So again, this is the real molecular orbital, what it would look like, but again, we're representing it as a composite of 4 molecular orbitals. So just keep that in mind. I'll put the real orbitals, what they actually look like up on your screen when we get done here. So, but I'm just going to draw the representations that you'd be on the hook for. All right, so moving on to psi 2. So actually, you know what? Before we move on to psi 2, let's just jump straight up to psi 4 star. So your lowest energy one, your orbitals are in phase all the way across. Whereas we're going to find out with your highest energy one on the diagram, they're just going to be out of phase all the way across. They're just going to alternate all the way across. And so in this case, to get 3 nodes, you'd end up needing a node in between every single set. And that's why they're just going to alternate all the way across. All right, so there's your lowest energy one, psi 1, and then your highest energy psi 4 star antibonding. And those are often the easiest ones to draw. It's the ones in the middle that can start to trip you up. Now, with 1,3-butadiene, it's not going to be too bad. So, but with 1,3,5-hexatriene at the end of this section, it's going to kind of be a little bit of a pain in the butt, as we'll see. All right, so moving on to psi 2 here. Psi 2 needs one node, and it turns out these nodes are symmetrically distributed, just like your nose is symmetrically distributed on your face. What I mean by that is your nose is right in the middle of your face. It's not off to the left, it's not off to the right, it's right down the middle, and so should your nodes be symmetrically distributed as well. And so you only have one nose, and it's right in the middle of your face. Just like in this diagram for psi 2, it's got one vertical node, and so that should be located right down the middle of the diagram. And so when you're filling in your molecular orbital diagram, if you don't cross a node, then your wave functions should match. But when you cross a node, that's when they're out of phase and don't match. Cool. And just fill in the other half here. Cool. And so sometimes we even go so far as to like identify when they're in phase. Call that a bonding interaction? So we'd have a bonding interaction here and here, and then an anti-bonding one here where we created a node. And so because there's 2 bonding and 1 anti-bonding, overall it's a bonding interaction. Well, the truth is, you could look at it that way and there's nothing wrong with that. So the truth is the midpoint of the whole energy diagram is kind of like the non-bonding line. That's where non-bonding electrons, like a lone pair would be. They're not part of a bond at all. So anything lower in energy that, pulls the atoms together in its bonding. Anything higher energy that would actually serve to pull the atoms apart if there's electrons there, and it's anti-bonding. So that's kind of where those names come from. Now, go into psi 3 here for a second. So psi 3 is going to have 2 nodes, and a little trick for putting in 2 nodes is to cover up half your diagram. And so in this case, I'm going to cover up half my diagram, so the halfway point's right in the middle there. I'm going to cover that up, and then cut that half in half. And if we cut that half in half, notice it's not cutting like halfway between this orbital and this orbital, but halfway between the very end and the middle here. So it's not exactly halfway in between there, but it's probably just a little bit closer to the orbital on the left than the orbital right, but it's still going to be in between those 2 orbitals is the important thing. And so we got a node there, and if we cut the other half in half, then we end up with another node right here as well. And once again, then we can just shade in appropriately. So again, when you cross a node, alternate. And if you don't cross a node, then make sure they're in phase. Cross a node, alternate. Cool, and there's the complete molecular orbital diagram for 1,3-butadiene. So, and you're on the hook for this. You could be asked to draw any one of these. You could be asked to draw the entire diagram. They could just ask you to draw psi 2. Or instead of saying psi 2, they could say draw the HOMO for 1,3-butadiene, and you have to figure out, oh, psi 2 is the HOMO. It'll have one node and looks exactly like this. Those are the kind of questions that might arise. Now, one other thing I want to set the groundwork for here. So when you look at these orbitals, you can also label them as being either symmetric or antisymmetric. And what that means is if you look at the orbital, so if you look at the right side and the left side, if they are the perfect mirror reflection of each other, we refer to that as being symmetric. So this one here is symmetric. Whereas if you look, and if the left-hand side and the right-hand side, if they're the exact opposite of the mirror image of each other, then we refer to that as being antisymmetric. And so it turns out if you've got an even number of nodes, that's the number of times that it flips them back as you go across, alternates, if you will, wave functions, the signs, as you go back and forth. If you've got an even number, then you're going to have no choice but to be symmetric. The left-hand side would be the perfect mirror image of the right-hand side. But if you've got an odd number of nodes, well, then you're going to flip one extra time, and so actually they end up being the exact opposite of the mirror image. So notice my left-hand side is not the exact mirror image of the right-hand side, it's the exact reverse of the mirror image. And so that goes back to being antisymmetric. And so you find out they alternate this way all the way across. Your lowest one's always symmetric, and then antisymmetric, then symmetric, then antisymmetric, and they always alternate like this. Notice it's also true back here. So psi 1 here is symmetric, psi 2 antibonding, antisymmetric. It always works that way. That's not so important for this lesson on pi molecular orbitals. However, I will allude back to this when we start talking about the pericyclic reactions at the end of this chapter. So super important for understanding an aspect of those reactions later on. Cool. That is 1,3-butadiene. That's kind of the classic introduction to pi molecular orbitals where it occurs with. And again, we're going to take a look at the allyl system in the next video, and then we'll take a look at 1,3,5-hexatriene in the one after that. Now, if you found this lesson helpful, would you consider giving me a like and a share? A couple of the best things you can do to support the channel and make sure as many eyes as need help with this material see this video. If you're looking for the study guide that goes with this lesson, if you're looking for practice problems, if you're looking for a final exam rapid review for your OChem final, check out my premium course on chadsprep.com. A free trial is available.